So we were talking about cleavage. Cleavage, once again, does not involve breast or mammary glands. That's a different kind of cleavage altogether. But with minerals, cleavage has to do with planes of weakness. Okay, and if you have cleavage, it means it breaks smoothly along planes of weakness. For example, calcite has this shape here, and it has weak bonds here, and it has weak bonds across the top and here. It would also have another dimension going back into the thing where it breaks. And so these planes of weakness cause it always to break and forms these kind of rhombus shaped pieces like this. Look like a rectangle that's been kind of pushed over by the wind. Okay, and they will always break along those. Another extreme example of cleavage would be mica. Mica forms in sheets, and the chemicals are held together very strongly along the line, but there is no cross connections, and so you can peel it off in layers. And when these layers peel off, then that's because of the fracture. In fact, in some places, very large and lighter colored mica, they could peel off big sheets, and they would use them for windows because they didn't have glass on prairies, and people are settling out far away from civilization. And a lot of times they would just simply use those for windows because of the way they cleavaged. All right, and so that's just the idea of cleavage. Now, fracture means that there are no bonds that are weaker than the others. They're all about the same, and so it's just kind of randomly where it breaks. They're random. They have no particular shape that they break into, and so fracture is just meaning it has no cleavage, basically. So if it has cleavage, it has a certain pattern that always breaks into the same shape, and no matter how small pieces you break it into, it'll still break in that small piece, but fracture will not. The next thing we'd like to look at is luster. Luster really just has to do with what the surface looks like. Okay, and based on how it reflects light, it could be metallic, which would be very shiny, silvery, gold, whatever, bright colors that reflect well. Pearly or iridescent, sometimes we use that as an example of a luster. Here are some different ones here. Hang on, let me try to draw up the picture here. All right. And you can see some of these have different crystal shapes, but also you can see a luster. Okay, that would be more maybe like pearly or iridescent kind of luster. Okay, this is asbestos, which is all stringy and breaks into little strings. But luster just means what does the surface appearance look like. Okay, now that is different than next one is color or streak. Color is fairly obvious. If you look at the mineral, what color is it? Is it yellow? Is it gold color? Is it silvery colored? What color is it? Okay, not so much have it shiny and that kind of thing, but just what color actually is it? Now, the color is probably one of the least least reliable characteristics, because even though we say that minerals have a certain chemical structure, okay, it can vary a lot depending if there's impurities in it. For example, aluminum 2O3, aluminum oxide basically. If it's white or grayish color, it's called corundum. But if you get chromium impurities in there, it becomes rubies. If you have iron or titanium, it becomes a sapphire because it changes the color. As a kid, when I was trying to learn rocks, which I live in the Panhandle, there weren't very many rocks anyhow, so that was discouraging. But it was discouraging. I started looking at, well, you couldn't tell because they could be this color, or this color, just depending on what impurities were present. So color is not a very consistent one. However, streak, on the other hand, is very good. Streak is where you take the mineral and you grind it along usually a porcelain tile, a little piece of tile, and you look at the color that it leaves behind. And the color that it leaves behind may not be the same color. It may be like a dark mineral, but then when you grind it to powder, it looks red or yellowish. Okay, and so the streak may be different than the color, and usually the streak tends to be a more reliable characteristic. But color in general can vary a lot from one to the next. The last one we want to look at here is the density. Okay, and we've probably mentioned density before. Density has to do with, usually we talk about the heaviness, okay, of a mineral. All right, but heaviness could obviously depend on how big the piece is, but we're really talking about the compactness. If it has a lot of stuff, mass, compactness, I would say compactness. If you're going to make up words, you can at least make up how you spell them, right? Compactness. In other words, if you have a lot of matter crammed into a small amount of space, it's going to feel very heavy, very dense. What we're saying is there's a lot of weight in a small space. On the other hand, if it has it takes up a lot of space and it feels very light, then that's going to be very undense. Okay, and that's really all we're talking about if it has to. And that's the ratio of density is just the ratio of mass to volume. Okay, if you're doing this, a chemical formula, it would be mass divided by volume. So the more mass you have in a small amount of volume, the more dense it is. And that is a fairly consistent value, and therefore is much more of use, for example, than say color for identifying which type of mineral you have. Now, I want to talk for just a second about the difference between minerals and rocks, and this gets a little confusing because it is confusing. All right, but sometimes there is no difference. Okay, for example, quartz, which is silicon oxide. Okay, it's a mineral. It forms crystals. It has a particular formula that it always forms. Okay, and although it can have impurities and be different colors. Okay, there's rose quartz, there's milky quartz, there's white quartz, there can be purple quartz, there can be different colors, and that's why you get all these geodes with, they're usually quartz crystals, but they can be all kinds of different colors depending on the impurities. But there's also quartz rocks. Okay, in general, the definition of rock is it's made of two or more minerals. So if you put a couple minerals together, rocks are made out of minerals. Having said that, there's rock salt, which is halite, which is a mineral, considered a mineral because it is a pure substance, and it has the same composition, NaCl. So it's salt, and it's a mineral, but it's also it comes in such large quantities that sometimes it's called a rock. Same with quartz. It's silicon oxide, but if there's a big enough chunk of it, we would probably call it a rock, but it can be a mineral. So some things are minerals, but there also we'll find rocks that are called the same thing. But most rocks contain several different minerals, so they're not a very specific composition. They can be several minerals mixed together. All right. Now, as you can see, that probably makes it a little difficult to name rocks sometimes because they may have more of one kind of. Two rocks of the same kind may have slightly different amounts of different minerals in them, and so usually there's kind of a comparative scale. As it gets to be more of this one or less of that one, then we call it a certain thing. But I don't want to confuse it all, but just keep in mind rocks are made of usually two or more minerals, but there are some minerals that are present in such large quantities and big chunks that they are considered rocks also, and you'll see them listed. So I apologize for that ahead of time because that gets a little confusing and doesn't simplify things, but that's just the way it is. All right. When we classify rocks, very often we classify them by the minerals that make them up. Okay, and there are two very large groups. One are the silicates. Silicates tell you right off the bat that it is going to be made out of silicon and oxygen. Okay, and so some combination of silicon and oxygen, and then possibly something else added to it. Okay, and we'll talk more specific about that. The other ones are non-silicates, which obviously are everything else. Okay, so they can be anything else besides that. And we'll talk about some of the groups that make them up here in a minute. But let's talk about silicates first. Okay, silicates are roughly about 90% of the Earth's crust. All right, so almost the whole Earth is the crust, the outside layer. First couple miles of rock material is silicates. Okay, there are two main types. We break them down into obviously part of them is going to be SO4, which is silicate, but there are the ferromagnesium, all right, and you can see a trend here, the non-ferromagnesium. All right, ferro means iron. Magnesium, you can guess, probably means magnesium. All right, we know that was one of the more common elements. So if it contains iron or magnesium plus silicate, then it's going to be a ferromagnesium. These rocks tend to be very dense, very heavy rocks, which makes sense. You got iron, magnesium is fairly dense too. Okay, and they tend to be fairly dark. So if they're dense and dark, double D, not Dungeons and Dragons, but in this case, dense and dark, then it's going to be a ferromagnesium. A non-ferromagnesium, then, guess what? Is not going to contain iron. So very little or no iron and magnesium, and they tend to be very light, not dense. Okay, so they're also light colored. So they're light colored, but they're also less dense. So they're really just double light either way you want to look at them. All right, very light. Okay, extremely light. So anyhow, and so these minerals are going to be things like, for example, one of those common minerals here is called feldspar. Feldspar contains either aluminum, sodium, potassium, and or calcium plus silicon. Whoops, put that there on the I. Silicon oxide. Okay, and so they make up about 50% of the crust. All right, that means it's about 40% up here, and with a ferromagnesium. All right, now the other main groups, this is basically got something plus silicon oxide. The other main part of the non-ferro is just quartz. Okay, and quartz is just SiO2. In other words, it's just silicon and oxygen. And most sand is made of small pieces, and usually it's quartz sand. Okay, and so it's one of the most common minerals around. So you can see why silicon and oxygen are such a big part of the Earth's crust, because you have the ferromagnesium and the dense dark ones that have iron and magnesium plus silicate, and then you have the non-ferro ones such as feldspar, which have one of these elements plus silicon, and then you have quartz, which is basically just silicon and oxygen. And so that's why they're such a big part of the Earth's crust. Okay, so silicates are 90% of the crust, and 50% of that is the feldspar ones, and then the quartz also would join in there. Now, if we put all the non-silicates together, that's the other group, all the ones that don't have silica, which is silicon and oxygen in them, they make up about 8% of the Earth's crust. All right, and so you got 90% is the silicates, and about 8% of is this. Now, these are named by their formula. If it contains this ion, then it would be a carbonate. Okay, just like when we named elements, remember carbon plus oxygen would be called carbonate. Some of these common ones would be calcite, a very common mineral, and that is calcium carbonate. Okay, if you have magnesium carbonate, that would be known as dolomite. Okay, and that's another common mineral. The next one we have sulfides. Sulfides are a metal plus sulfur. Oxides would be a metal plus oxygen. And many of the mineral ores that we dig up to get iron and stuff would be like iron oxide, copper oxide, or sulfide. And so the sulfides and oxides are the ore-forming minerals, or chalcogens, we said on the column up on the list. And so that's why, since they join up with metals, many of the metals we get come from these rocks that these form. Ugh, there we go. Spit it out. All right, and so we'll stop right there. There are still some more non-silicates, so no, we're not done yet, but we'll get to them in the next video.